Hello and welcome back at long last to the Cryptopals Guided Tour. My name is Eli, I'll be your guide. In this video we'll be taking on Challenge 17 from the start of Set 3. This challenge is a spin on the classic padding oracle attack, which is one of my absolute favorite crypto attacks, and it's one that shows up in the wild surprisingly often. Now if you prefer reading over watching videos, you're in luck. I have a pair of blog posts, one of which inspired this series, the other of which was inspired by it. The first of these posts is a quick introduction to the padding oracle attack, and you can find it by googling padding oracle. This post was a direct precursor to the guided tour. I wanted to write a series of deep dives in this style, but I quickly realized that videos would work better for the amount of information I had to share. The second post actually grew out of the background research I did for this video. I wanted to discuss how the attack changes when your oracle is less than perfectly reliable, but I realized I couldn't find a good primary source on that, so I looked into the problem myself and wrote one. But that's enough backstory, let's get to the crypto. In this attack, we'll be exploiting a very small information leak. Let's start with the big picture view. The setup is the defender comes up with a plaintext, which they encode, pad out to the block length, and encrypt with AES CBC. They take the result and provide it to the attacker. So far, so good. Now we are the attacker. Our goal is to decrypt this message. How is that possible? Well, in general, it's not, because we don't know the key. We need some kind of toehold here. However, a very small toehold will do. For instance, what if we could get the defender to decrypt a message for us, then tell us whether the plaintext has valid padding or not? Now, this might seem unrealistic, but you'd be surprised. It is still quite common for systems to leak this information by accident, and a recurring theme in cryptography is that small information leaks can compound into big attacks. The padding oracle attack might just be the most famous variation on this theme, although it does have some competition from, say, Blankenbacher's attacks on RSA, which we'll cover in a later video, but I digress. We're here to talk about padding oracles, but before we get into the attack itself, let's take a quick detour to observe a padding oracle in its natural habitat. Suppose you're reviewing an API for a website that keeps track of its users using encrypted tokens. Luckily for us, the developer thought this idea was simple enough that they could get away with rolling around crypto. Here's what they're doing. First, they take some encoded data about the user, some of which might be secret from the user. Then they encrypt this data under AES CBC using a key that is only stored server-side. They concatenate the resulting IVN ciphertext, then they send this blob to the user. As the user, we don't know the decryption key, so we can't immediately decrypt this, and we're not meant to. The idea is just that we save this ciphertext and include it in future API queries. When we do this, the server will be able to decrypt it, read the contents, and learn all about us. This is kind of like a worse version of a JWT. And so far, this is all well and good, but what happens if we provide an invalid token? What if we just make one up? There are two main error cases here. The first is when the padding is bad and the decryption fails, which is the most likely outcome. The second is when the padding is valid. In this case, the data is probably still garbage, causing the deserialization to fail. In both of these cases, our query fails and we get an error back from the server. That's fine though, because we're not interested right now in making this query succeed. We're just interested in finding out how it failed. In this example, it's easy because the server just tells us what happened. If we see decryption failed, we know the padding is invalid. If we see deserialization failed, or no error at all, then the padding is valid. This gives us a padding oracle. So this is exactly the kind of toehold we need to launch our attack. If we can make enough queries to this oracle, we can decrypt this token. But that's not all we can do. We'll also be able to make arbitrary modifications to the token, or even encrypt entirely new messages under the secret key, all without ever learning the key's value. Now we're about to get into the details of how this attack works, but if you'll bear with me, I want to take the long way there, which starts by talking about why this attack might seem like it shouldn't work. The reason why I want to do this is because cryptography is a field full of counterintuitive results, and if you just hear someone explain them straightforwardly and uncritically, it can be easy to forget just how strange and surprising some of this stuff really is. So just to counteract that effect, and for an extra bit of dramatic flair, let's put ourselves in the shoes of a developer who gets paged at 2 a.m. to fix this vulnerability, and who wants nothing more than to go back to sleep. Here are some of the things that developer might say to try and downplay this issue. First off, like we just saw, a padding oracle tells us whether or not any given ciphertext decrypts to a plaintext with valid padding. That is to say, all we get is a yes or no answer to a small simple question. And in fact, it turns out the answer is no for about 99.6% of all possible ciphertexts. So, because this answer is so biased, the information leak here is very small. Next up, intuitively, all we have is a ciphertext, so surely the attack must involve modifying the ciphertext. But for any good cipher, these modifications will have unpredictable effects on the plaintext. Now that last statement assumed that we don't know the key, so we might as well add that as long as our cipher is good, there's no clear path to key compromise here. And as for the actual information we're leaking, that seems pretty insignificant too. After all, padding usually only appears in the last block of a message, so this oracle can only tell us about that last block. And finally, padding bytes and message bytes do not overlap, so the oracle can't even tell us about the message bytes. or at least so it appears. All of this seems to point towards this attack not working. I could go on, but you get the idea. The thing is, all of these points are true, but none of them actually matter. The attack still works. And this is something I really want to emphasize. In cryptography, beware of intuitive arguments. There are many fields where you can get away with or are even encouraged to use this sort of heuristic reasoning. This is not such a field. This is why we care so much about things like formal verification, proofs of security, and so on, because it's much easier to trust an argument when it's backed up by mathematical rigor. Although even there you still have to be careful because subtle mistakes in proof are easy to make and hard to find, and they can lead to real breaks in supposedly secure systems, as we have seen here at NCC many times. But anyway, let's go ahead and call these points what they are. They lack rigor, so they're not actually problems, they're just complaints, and we don't care about complaints. So now that we've ruined this developer's night, let's see what it is that they're so worried about. Let's take a look at the attack. Once again, this right here is CBC encryption. If you've been following the guided tour, then by now this figure should look very familiar. The key point to notice here is that each plaintext block is XORed with the previous ciphertext block or IV prior to encryption. For this attack, we won't be spending a ton of time with this multi-block figure because it turns out that the multi-block case of this attack reduces nicely to the single block case. To see why, let's review CBC decryption. We'll just flip these arrows around and there we go. In this figure, we know the ciphertext, but not the plaintext or the key. We'd like to find the plaintext, but to do that, we need to be able to compute d sub k, which of course depends on the key k. Now, we don't know k, but the defender does. And so the strategy for this attack is to get the defender to compute d sub k for us, and then to trick them into revealing information about the result to us. Now, this attack is usually called a chosen ciphertext attack, which is not wrong because it can be carried out in the ciphertext, but it can also be carried out in the IV, which is what we'll do here because I think this is more clear. We'll be leaving the ciphertext unchanged and messing around with the IV instead. So we'll take this ciphertext block, isolate it, and fill in a new IV in plaintext. This IV is attacker controlled, and we could set it to whatever we want, but for now let's keep things simple and just set it to 0. I'm leaving the ciphertext block blank here because its contents would be essentially arbitrary, and because I don't want to distract from what's important about this attack, which is the interaction between the IV and the output from d sub k, which we'll add a block for right here. Now, if we send the defender a ciphertext and an IV, the defender will compute the rest of this diagram. Of course, they don't tell us the result, they only tell us whether or not the result has valid padding. If the padding is valid, that could mean one of 16 things. It probably means the plaintext ends with 1 byte of value 1, but it's also possible that the plaintext ends with, say, 2 bytes of value 2, or so on. However, these possibilities are not all equally likely. For a uniformly random plaintext, the odds of getting valid 1 byte padding are 1 in 256, whereas the odds of getting valid 2 byte padding are 1 in 256 squared, and it drops off exponentially from there. So even though longer padding is not likely, it's still likely enough that our attack will have to take this possibility into account because we can't rule it out entirely. Now, the first key insight in this attack is to recognize that by making modifications to the IV, we can predictably modify the plaintext. You might recall that earlier we were complaining about how we don't know what will happen to the plaintext if we change the ciphertext. This is true, but the same is not true for the IV. Changing the IV changes the plaintext in an entirely predictable way. To be specific, flipping a bit in the IV will flip the corresponding bit in the plaintext, and setting the IV's final byte to any value will XOR that value into the plaintext's final byte as a trivial corollary. This is exactly the same property that we took advantage of in Challenge 16. In this context, we'll use this property to launch a search. We'll loop through each possible value for the last byte of the IV. In effect, this also loops through each possible value for the last byte of the plaintext. It might take a while, but we know that sooner or later we'll set this byte to value 1, or to another byte that constitutes valid padding, and we know that once this happens, the oracle will tell us. Now, just as we discussed, technically we don't know the length of the padding, we only know that it's valid. The most likely outcome by far is that it's a single byte of value 1. That said, it could also be 2 bytes of value 2, and so on, up to 16 bytes of value 16, and the only reason that we're ruling out longer padding strings, which technically are allowed, is because they simply would not fit in this buffer. As for the longer padding strings that we are considering, we can rule out these edge cases by changing the penultimate byte of the IV. If the corresponding byte of the plaintext is part of the padding, then changing it will cause the padding to become invalid. Contrapositively, if the padding is still valid, then it must have length 1 and therefore value 1. If this test fails, we'll continue the byte search, but if it succeeds, then we've recovered the exact value for the final plaintext byte. Now, XOR has some useful algebraic properties, which you can read about in the bottom left if you're into that kind of thing. Otherwise, just trust me when I say that we can turn these arrows around without invalidating the diagram. Then we just compute the XOR of the IV in plaintext, write it down, and just like that, we've recovered the last byte of d sub k's output. So we just made length 1 padding. Now let's try to make length 2 padding. We'll use the same XOR algebra as before to set the final byte of the plaintext to value 2, then we'll search through each value for the penultimate byte until we get a hit from the padding oracle. Note that this time we don't have to check the length of the padding. Since we set the last byte of the plaintext to value 2, we know for a fact that any valid padding must have length 2. Now, using the same algebra as before, we can recover the penultimate byte of d sub k's output. From here, the attack proceeds just how you'd expect. We set the 2 final bytes to value 3, then search through each possible value for the anti-penultimate byte until we find the value that works. As you can probably guess by now, we repeat this search for each byte until we've recovered all 16 bytes of d sub k's output. For each step, we're deriving an IV that sets the final n-1 plaintext bytes to value n, then we're searching through the nth from last IV byte until we hit valid padding. We take that IV byte, XOR it against n, and that's our d sub k byte. If you squint just right, this might kind of look like our byte-at-a-time ECB decryption oracle. Of course, it's not exactly the same, but it's fast for the same reason, namely because the attack proceeds 1 byte at a time and therefore only has to deal with bite-sized search spaces. We've now pulled off a padding oracle attack. We've recovered the full output of d sub k, and we've done this without any knowledge of k. I mentioned earlier that the multi-block case of this attack reduces to the single-block case. Now that we've covered the single-block case, let's bring this result back to the multi-block case and start putting the pieces together. And just like that, we know how to recover these cipher calls outputs. Given those outputs, we can, of course, now recover the plaintext of any message encrypted with this key. So let's work an example. Here's a sample ciphertext and IV. We'll start with the second block of the ciphertext. Running the padding oracle attack on this second block allows us to recover the output from the second call to d sub k, 1 byte at a time. Once we have that, we just evaluate this XOR, and the suspense is almost over, but not quite, as we discover that the second plaintext block is in fact a full block of padding. Moving on to the first block of the plaintext, we run the attack again, and we see that it decrypts to our favorite 1-block string. So there we have it. That's the padding oracle attack, or at least that's the simple version of it. But there are still some unanswered questions here. Probably the biggest one is, how can you prevent this attack? That question has a short answer and a long answer. The short answer is use authenticated encryption. And we'll get to that, but let's take the long road there. To get on the long road, let's start by doubling back to our example from earlier. We had a web service with a custom token-based authentication scheme. The backend for that might look a little bit like this, at least if we're using Flask. The choice of framework is kind of arbitrary. I just like Flask because it's terse. In case you aren't familiar, let's take a lightning tour. I'll try not to spend too much time on this, so I don't bore you if you already know it, but we'll start at the top here. This function handles requests for the /index root, as we see from this app.root decorator here. Request context is exposed to the handler through this request object. We use this to get the token byte string, which we assume will arrive hex encoded. Of course, this code throws a 500 error in a few cases, but we'll gloss over that here. Moving on, we split the token into an IV and a ciphertext, which we hand off to AES. In this case, decryption is treated as a separate operation from unpadding, which happens down here. If unpadding fails, we return an error. If the padding is valid, we treat the unpadded plaintext as JSON and try to deserialize it. Again, if this fails, we return an error. If the JSON is valid, though, we're good to go. The endpoint doesn't actually do anything because that's not the point. The point is just that this endpoint has a padding oracle. In this case, it's a very simple and reliable oracle. Decryption failed means bad padding. Anything else means good padding. We've just seen what the impact of an oracle like this can be, but how do we fix it? Again, the correct answer is to use authenticated encryption, but for now let's pretend we don't know that, or maybe it's not an option. Well, if the attacker's oracle works by distinguishing between these error cases, then our first attempt at a fix should just be to combine them. This is a big improvement. The error message no longer specifies whether we hit bad padding or bad JSON. However, this is still not perfect because this code is not constant time. Now, some of you will immediately know what I mean by that, but not everyone will, so let's dig into it. We have two likely cases here. In the first case, the function returns after throwing an exception here. In the second case, the exception is thrown here. It technically could also return down here, but this doesn't actually matter for our purposes. The point is that the time it takes for this function to return depends on which exit point it takes and how much work it does in the process. Does it execute just these statements, or does it execute these ones too? The latter case will take very slightly longer. This difference is very small, and in this example it would require a lot of measurements to compensate for measurement noise. That noise could come from the network, from server load, or from any number of other sources. However, there are methods for overcoming this. The simplest one is just to increase our sample size. By doing this, we can reach nearly arbitrary levels of precision at the cost of speed. We can make this much more efficient by applying statistical methods, and we'll touch on that later in this video, and we'll really dig into it at the end of set 4 when we implement our own timing attacks. But for the moment, let's focus on spotting padding oracles. We've already determined that this function is not constant time, regardless of whether or not the functions it calls are all constant time. However, the situation gets even worse because it turns out that those functions are not constant time either. What that means is that even if the calling code was constant time, we'd still have problems here. Now, JSON deserialization, I'm not even going to go there. There's basically no way that I know of to get that right in the general case. It's just obviously not going to be constant time. It might be more interesting to look at the unpad function. Now, to be fair, in general, it's not possible to unpad plaintext in constant time either. You can validate it in constant time, but unpadding is going to involve secret-dependent memory access patterns, which are not allowed in constant time code because of concerns related to caching. So on a theoretical level, we wouldn't expect this to be fully constant time, but let's look at the code anyway. We'll treat it as a sort of a case study. Now, this might seem excessive or even needlessly cruel, but I just want to drive home just how common this kind of issue is. Most people who don't look at this stuff for a living tend to underestimate how common or important this is. This function comes from PyCryptoDome, which is a great library that I often recommend, and I'm not doing this to give them a hard time. It's not, oh, look, they messed up. It's more, oh, look, even they have these issues. So here's the unpad function. This function has a lot of cases, but since we're using PKCA7, we can focus on this block here. We get the padding length here, and this is so far so good. The padding length itself is secret data, but its location within the plaintext is not secret, so we can access it safely. Next, we have some bounds checks, which are fine, but after those, we get to this line. Here, we're slicing into the padded data to get the padding bytes. This will allocate a new bytes object sized to the padding length, and then it will copy the padding bytes from the old buffer to this new one. All of these operations depend on the padding length, which is secret, so this is not constant time. The same thing happens over here. This bchar function is fine, but then its return value gets extended out to the padding length. So again, we're allocating and writing memory based on a secret value, so that's another timing leak. And of course, the comparison here is not constant time either. It'll finish executing as soon as it finds a mismatch between its arguments. Of these three issues, the comparison is actually the smallest issue and also the easiest one to fix. There's a function in the standard library called secrets.compareDigest that could be used as a drop-in replacement for this equality check. Secrets.compareDigest is really a generic constant time buffer comparison, but they borrowed it from their HBAC library, and the naming of it reflects that. They decided to name it after the specific use case of comparing digests. However, even if this change was made, the other two issues would still remain, and in general, they are not so easy to fix. To be fair, these timing side channels are quite small. If you were trying to measure this over a network, the ratio of signal to noise would be very heavily biased towards noise. That said, this is not entirely impossible to exploit. The attack would just be very slow. So what can we do about this? We've just seen that while we can make this timing side channel very small, we can't eliminate it completely. What we can do is prevent it from being exploited. Recall that the padding oracle attack is a chosen ciphertext attack, so we'll just prevent the attacker from choosing ciphertexts. We'll do this by introducing message authentication codes. In modern crypto systems, authenticated encryption is the norm. CBC mode by itself does not provide authentication, but we can fix that by bolting a MAC onto it. Given the choice between doing this versus using a cipher mode that provides authentication by default, like GCM, I'd say use the authenticated mode. This is because with authenticated modes, you don't have to handle the MAC yourself. In fact, what I'd really say is to use an authenticated stream cipher, like ChaCha20 Poly 1305, but we'll get into that in a later video. Now, a rookie mistake here would be to just MAC the ciphertext. As we've seen, we have to cover both the ciphertext and the IV because the attacker can use either of them to carry out this attack, and just as a general rule, there aren't many reasons to pass up integrity and authenticity checks. It's just common sense to authenticate everything you can, except maybe if you care about deniability. And even if you do care about deniability, you still might be better off just using a MAC and just disclosing the MAC keys after you've used them. Strange as that might sound, it does work, and you can see it in action in the OTR protocol. Now, there's a whole other conversation that can be had about whether deniability is useful in practice, and in fact, there was a good talk about this at Real World Crypto 2023, but we won't go into that here. Anyway, once we compute the MAC, we'll just append the result to the ciphertext. Note that we're macking the ciphertext, not the plaintext. This is an important distinction and a subject of some controversy. I won't get into that here, although you can Google it if you want. I will, however, say that macking plaintexts is a surprisingly common mistake that has been recommended and implemented in some high-profile cases by people who really should know better. Anyway, MACs are keyed, and the attacker can't compute the MAC without knowing the key, so the server, who knows the key, can just recompute the MAC from the ciphertext and confirm that the tag on the message matches what they computed locally. If it doesn't match, then the attacker has tampered with the message. If it does match, then they have a reason to believe this message was created by someone with knowledge of the key. Now, of course, this doesn't prevent replay attacks, but as long as you implement it correctly, it does prevent attackers from making up ciphertexts and passing them off as authentic. This is sufficient to prevent padding oracle attacks. Now, a quick word about key management. Technically, we could reuse the encryption key as a MAC key, and it would probably be fine. That said, it also feels like it invites trouble. We would say that if nothing else, this is bad cryptographic hygiene. The best practice here is to use separate encryption and authentication keys, just so that there's as little coupling between these algorithms as possible. Given a single key, these specialized keys are easy to derive. For example, we could use a KDF, or just take some domain-separated hashes of the top-level key. We won't worry about the details here. We'll just write K prime for the MAC key and K for the encryption key, and we'll leave it at that. As another note, we haven't specified a MAC function here. That is intentional. There are plenty of choices, but in practice, people who like CBC seem to like pairing it with HMAC. The main disadvantage of this construct is its speed, or lack thereof, but while CBC with HMAC falls short of being the absolute best, it's usually at least acceptable. That said, this still can go very wrong if you make a mistake, as we will see shortly. Before we get into that, just to recap, we've gone through a few layers of defense here. First, to make sure externally served error messages are generic. Second, validate padding in constant time and minimize the timing leak in unpadding. Third, and most importantly, you just back your ciphertexts so that attacker-crafted ciphertexts will be rejected as invalid. Now let's switch back to the attacker's perspective and look at these same defenses, focusing on how each one of them can fail in practice. So our first line of defense is minimizing the data leak. We give generic error messages, we get our code as close as possible to constant time, and so on. We might take further measures depending on what side channels we're worried about, but that depends a lot on context. For example, power analysis might be unlikely for attacking a desktop, but it might be very likely for attacking a smart card. There are tons of other interesting potential side channels, including EM radiation, acoustic signals, and so on, and that's a very fun rabbit hole to go down, but it's a bit far off course for this video. At the very least, though, we know timing side channels are almost always in play. Now, we'll do a deep dive into those when we get to challenges 31 and 32. For now, let's abstract away the specifics of our side channel and just say that we can get a somewhat reliable padding oracle from it. It might not be perfectly reliable because these channels contain some amount of noise, which can throw off our measurements. So this brings up a question. As our side channel gets less reliable, how does the attack change? Is it prevented? Does it become impractical? In particular, does a less reliable oracle necessarily lead to a less reliable attack? Surprisingly, it turns out that the answer to this last question is no. As for the first question, that one is a slightly longer answer, but let's give it a shot. Let's ease into it with some simple cases. Suppose we had an unreliable oracle that sometimes gives false negatives. Whenever we give it invalid padding, it'll always give a correct answer, but sometimes it'll mistakenly tell us valid padding is invalid. Let's look at how this might change our byte search. I've reduced the search space from 256 elements to 16, so it fits better on screen. This doesn't really change the underlying ideas at all, it just makes them easier to see. We'll start by scanning through all 16 candidate byte values, sending each one to the oracle, and recording the responses we get. We'll stop when we get a positive response. With a perfect oracle, we can expect this to happen on our first run through the search space. However, since this oracle can give false negatives, we may need to make several passes through the space before we get a hit. This is trivial though, and we see that on the third pass, we find our result. Our second simple case is an oracle that only gives false positives. This time, we got a lot of hits on our first scan through the search space. Each time we get a negative result, we rule out that guess. Then we scan again through the positive results, building up a new shortlist as we go. Each scan reduces the number of candidates until eventually we're left with just one, at which point we know we found the correct byte. And it turns out that this intuition can be formalized. Let's add a second chart here for our confidence in each candidate. This chart tracks the probability of that candidate being the one we're searching for. At the start of the search, we don't know anything, so we consider each value to be equally likely. After our first round of queries, the oracle has given us 5 negative results. Accordingly, we adjust the probabilities for all those values down to 0, and to compensate for this, we raise all the remaining probabilities up to 1/11. This process continues intuitively enough until one of our options hits a confidence level of 1. You'll notice that I was updating the confidences after each round of queries because that's when it's easiest to figure them out. Similarly, if we were to chart confidences for the only false negatives case, after each round of queries, the confidences would all be equal until we finally got a positive result, at which point we take that value's confidence up to 1, while all the others go down to 0. So in these special cases, the confidences are easy to evaluate, but let's ask a leading question, which we won't answer immediately. Let's ask, what would these confidences look like in the middle of a round? In the false negative case, if you have 4 negative results for one value and only 3 for another, then surely the value with 4 negatives is slightly less likely to be correct, but how much less likely? Similarly, in the false positive case, if you have 2 frontrunners, one of which has more positive results than the other, you might consider that one more likely to be correct. But how can we quantify this intuition? We'll come back to this question, but first let's break out of these simplified cases and consider the combined case, where we have both false positives and false negatives. This is the type of noisy oracle you can expect to encounter in the real world, and knowing how to handle it is crucial to understanding this attack in practice. Let's set the confidence charts aside for the moment and just look at some outputs from this oracle. We see false negatives and false positives interspersed throughout the output. See if you can guess, by looking at these outputs, which value is the correct one. You might get it, but it's not immediately obvious how to make a guess here, or how confident we should be in our guess. After all, whenever we see a combination of positive and negative results, we know that some of those results must be errors, but we don't know which ones. In fact, no matter how many queries we make, we can never rule out this possibility completely. This is where a lot of work in the area has run into challenges, coming up with increasingly complex statistical tests to run on groups of queries in order to consolidate them into an overall result. This is a promising idea, but the methods I've seen ultimately end up relying on huge sample sizes to produce a reliable oracle, and then they make a large number of queries to this synthetic reliable oracle. Another option, which I propose in that second blog post I mentioned, is to try to create a reliable byte search out of an unreliable oracle. In other words, rather than trying to make the oracle reliable, we'll figure out how to use it directly in spite of its unreliability. But how do we do this? Well, I have some good news and some other news. The good news is that this can be done. The other news is that it involves math. Specifically, it involves a very famous result from probability theory known as Bayes' theorem. Bayes' theorem looks like this. I'll give you a brief rundown, but if you want the full details, I'll refer you to 3 Blue 1 Brown's excellent video on this topic, which I learned a few things from myself. I'm not going to try to recap it. Instead, what follows here is a very quick high-level overview. Bayes' theorem basically allows you to adjust your confidence in a hypothesis as you gather evidence related to that hypothesis. For a full byte search, we would have 256 hypotheses. Each hypothesis tracks the possibility of its corresponding byte value being the target of our search. We'll use Bayes' theorem to adjust each of these hypotheses after each oracle query. The first thing we'll do is expand the bottom of this fraction, which makes it harder to read but easier to work with. Now, for any given hypothesis, we have 4 cases to consider. The evidence can be for either the same value or a different value as the hypothesis, and it can be either a positive or a negative result. We'll indicate positive or negative results with T and F respectively. We will also assume that we know the false positive and false negative rates, which we'll call P1 and P2 respectively. For each of these cases, we need to evaluate each of the individual probabilities in Bayes' theorem. I'm not going to talk through these because personally I've never been the type who can follow along as someone reads math to me, and so I'm not going to be the type of person who reads math to others. That said, if you want to work through all the casework, I'd encourage you to do so, because it's really no harder than your average undergrad stats homework, or you can check out the aforementioned blog post where I do spell all of this out in detail. Now, given this, we have a mathematically sound way of updating our confidences after every single oracle query. There's one other topic to cover before we're done talking about math. Let's talk about information theory, and specifically about entropy. We can compute the entropy of any discrete probability distribution using this equation. This is useful to us because our confidences in each byte can be run through this equation, and the resulting number will give us a sense of how much uncertainty, so to speak, is left in our search. Taking this a step further, we know we have estimates for each input value of how likely a positive or negative oracle result would be, and we also know from Bayes' theorem how the distribution of confidences would change in either case, and now we know how to quantify the entropies of the resulting distributions. This allows us to find the expected reductions in entropy for each potential query, which you can also think of as the expected amount of information gained from said queries. We'll add a second chart here to track these expectations for each byte. This one uses a nonlinear scale because these values are very, very small. And now let's see what happens to these charts as we gather oracle queries. This is our unreliable oracle with both false positives and false negatives again. Look at how quickly most of the options are ruled out here. After a couple rounds of queries, we have a pretty reliable shortlist, and it's interesting to see how the expected information gained correlates with the change in confidences. Sometimes they move in the same direction, but not always. We'll come back to that. Anyway, after a few more rounds, it looks like we have a clear frontrunner here. We can continue iterating until this frontrunner reaches whatever level of confidence we're looking for. As we keep going, it becomes increasingly clear that a lot of queries are being wasted here, asking about bytes that we've already ruled out. So a natural next step would be to consider introducing some kind of guiding heuristic to cut down on this waste and speed up the search. And if we're looking for ideas for such a heuristic, we have 2 of them listed on the left-hand side of the screen. We'll try using the maxima from each of these charts to guide our search. Now, if we want to be efficient with our oracle queries, then it might seem intuitively obvious to query for the value that'll tell us the most, or in other words, the value that maximizes expected information gained. Here's an example of that heuristic in action. Interestingly, notice that it tends to avoid immediately following up on positive results, though it doesn't mind following up on negative ones. Roughly speaking, this is because a follow-up query on a positive result carries higher potential downside, since it might undo the increase in that byte's confidence, whereas a follow-up query on a negative result carries more upside for similar reasons. This behavior starts to shift as we gather more information and our level of confidence in the frontrunner bytes increases. We can see that this heuristic is already a huge improvement over the more exhaustive strategy. Now let's see an even bigger improvement. We'll take another go at the problem, but this time we'll let the confidences guide our search directly. This is a super simple heuristic. At each step, we'll just query for whichever byte currently has the highest confidence. We get a handful of false starts here, just like we did with the other heuristic, but this strategy handles those gracefully, and eventually it ends up in the right place. That was over too quick, so let's run it again. In the average case, the confidence-guided heuristic tends to require a few times fewer oracle queries than the information-guided heuristic, and the confidence heuristic is significantly less inclined to explore the entire search space unless it needs to. It hones in on promising bytes as soon as it gets a positive result, which gives it an edge over the information guided heuristic for large search spaces. Rather than ruling bytes out by querying for them and getting negative results, it is happy to rule them out implicitly by honing in on the most promising byte. All in all, this tends to work remarkably well. That said, while the confidence-guided heuristic is faster on average, it also has higher variance, meaning that the number of queries per search is less consistent than with the entropy-guided heuristic, or for that matter, with the null heuristic. That's because it is more willing to go down dead ends if they seem promising at first, as we can see here. Usually we're willing to accept this risk in exchange for the low average query count, but this is still worth knowing about. Anyway, all these dead ends get ruled out before our confidence in them reaches the cutoff threshold, and eventually we do find the correct byte. Now, how do we know it's the correct byte? Well, in this case, we know because I'm telling you. In general, we won't know this with certainty, but we can get arbitrarily close to certainty because our confidence threshold can be set arbitrarily close to 1. You might be surprised to learn that this is not even expensive. Once our distance from perfect confidence is low, lowering it by another order of magnitude costs only a small fixed number of oracle queries in the average case. In other words, we can reduce our distance from perfect confidence exponentially for linear cost, though of course, the exact cost depends on the oracle's error rate. So that covers the hard case where the oracle is unreliable. There's more to say here, but I don't want to get too sidetracked, especially since we'll be diving back into this topic when we get to challenges 31 and 32, where we'll be exploiting timing side channels with the end goal of MAC forgery. I'm planning for that video to go way further into the weeds on this stuff, so for now this should do. We have one more case of this attack to cover, and that's the case where MACs are added. In contrast to the hard case, I'm going to basically gloss over this one because explaining it in detail would mean going into MAC forgery and basically rehashing the same content that I'm planning for those future videos. That said, let's add a little context here. The padding oracle attack is also an attack on CBC mode specifically. CBC doesn't have authentication built in, so we have to add it ourselves. And as we mentioned earlier, people who use CBC tend to use HMAC for this for some reason. Now, HMAC is not fast, but it is a solid and reliable MAC. However, many APIs for it just give you a MAC tag and leave you to write the validation logic yourself. And if you aren't careful here, then you can still get into trouble. Now, the problem here is that this comparison does not happen in constant time. As a result, and as we'll see again at the end of set 4, attackers can use this to infer valid MACs one byte at a time for arbitrary ciphertexts. After recovering a complete MAC for their chosen ciphertext, the attacker can use it to bypass this HMAC check and continue their chosen ciphertext attack. From the attacker's perspective, the downside of this new attack is that it does require one MAC forgery per chosen ciphertext. This raises the cost of the attack by a lot. However, the same ciphertext can be queried many times without having to reforge the MAC, which means that we can collect large sample sizes for each query. And as we discussed earlier, a whole range of statistical tricks do exist for synthesizing these samples into a more accurate oracle. Nevertheless, this extra step does raise the cost of the attack by a lot. In monitored environments, this might be a problem for the attacker, otherwise it's probably fine, albeit very slow. In any case, the fix is simple. We just replace this comparison with a constant time one, and that solves the problem. But this makes for a very nice segue into our next topic, which is talking about how, as a defender reviewing service logs, we might be able to detect this attack while it's happening and try to... No, I'm kidding. It's time to write some code. All right, and just like that, we're going to jump right into it. Here is our familiar folder with all our challenge solutions thus far. We have, of course, one requirement, which is by Cryptodome, and by sourcing our virtual environment, we make sure that this is available to us in this new script that we're about to write. All right, and right off the bat, let's sketch out what we're going to have to do with this. We have two functions we need to write. The first one will pick one of these strings, generate a random AES key, pad the string out, and CBC encrypt it. The second function will decrypt it, check the padding, and return true or false, depending on whether that padding is valid. Now, I'm going to go and add a couple embellishments onto this. First off, let's generate the AES key at the top level rather than inside the function, because if we're saving it, it's simpler to just make it a global rather than be modifying global state within a function. That's just bad practice if you can avoid it. So we'll say, and of course, IV reuse is very bad. In this case, we're only going to be encrypting one message, at least to start, and so it's fine. And I do like having these defined next to each other. That feels well organized to me. One other thing we know we're going to need is this block size constant. Technically, we don't need this, but having this as a name allows us to reference it by name rather than referencing a magic number, which is always nice. We're not going to use it down here because the key size is not determined by the block size. However, the IV size actually is, so we can just pop that in there. We also have this totally bizarre list of 10 strings, although not as bizarre as Vim's insistence on doing double indents for list contents. That's pathological and I refuse. We are going to format this manually. Oh, and these will actually need to be byte strings because we're passing them to AES. Man, I'm all over the place. I gotta warm up here. All right, that looks good. Now, before we go any further, let's fix our imports from OS import urandom. And there's a few other things we know we're going to need, like, for example, our PKCS7 functions. Those came from challenge 9, so let's import that now. And then padding error is something we're going to be catching, so we'll bring all 3 of those in. Now, what else are we going to need? We're going to need to break our ciphertexts up into blocks before we attack them, so let's pull in our function for that. And we also are going to be doing some XORs. And while we're up here, let's do this as well. And what else do we need? Well, I guess base 64 decode, because, I mean, look at these, right? And we're going to be randomly choosing from these. So we'll bring this in. Now, I've probably talked about this before, but I don't remember. It's been a while since I made the last one of these videos. This is not a cryptographically secure choice. If you look in the random library, you'll see that this choice is a instance method on an instance of random, which is different from system random. So if you wanted a secure choice, then you would use system random. In this case, the fact that we're even randomly selecting these at all is a bit of a goof because these are supposed to be tokens. This pair of functions, yeah, let's actually acknowledge this really quick before we go any further. These encrypt and decrypt operations are basically mimicking the scenario that we discussed at the start of this video with a client-server model and encrypted tokens. So yeah, I'm not super concerned about the choice of RNG here because, you know, the very premise of it is there's a little bit of a fiction to begin with. So let's just run with this. Now, moving on with the challenge, we will, yeah, I guess it doesn't really outline the rest of it, does it? It just says you can find 100 web pages on how this attack works, which is true, although technically I guess it would be 101 now, as soon as this video goes live. But yeah, let's just sketch out the rest of the attack here, then we can fill it in. And I'm going to add an index argument to the encryption in case we want to specify which one of these we want to get. And it'll choose one at random when this is not given. It'll otherwise respect our request. And for the decryption function, I think I'll do this slightly differently than they suggest to do it. I'm going to decrypt in 2 steps. And the first step is going to be a reliable, never fails decryption step that does not perform unpadding. And then I'll perform unpadding within a dedicated padding oracle function that calls this decryption function. And I actually have mixed feelings about this because by putting the IV, so traditionally you would put the IV before the ciphertext in your arguments list. That just, it goes first in when they're concatenated. It's just a standard practice, or not standard is the wrong word. It's just one of those things that people do. In this case, I have an IV value up here and I want to use that, which means that this needs to be a default value. Basically, okay, look what happens if I swap these, right? This is annoying. This is actually an error, and the linter will tell me non-default argument follows default argument. So if we wanted to have a default ciphertext, this would be okay, but we don't, of course. So the IV kind of has to come second, or it has to not have a default value. And so I'm kind of torn on this. You know, no, I'm going to relent. I was planning to do it like this, but I just can't. I can't look at ciphertext followed by IV. You got to draw the line somewhere. So we'll provide this when we call this, and that'll be good enough for now. And yeah, this padding oracle function will call dec and then try to unpad the result, and it'll let us know how that went. And then for the attack itself, as we discussed, there's a single block case and a multi-block case. The multi-block case reduces to a series of runs through the single block case. And so I think we can just define one function for each one of those. And again, I'm debating with myself, as I really need to make these decisions ahead of time. I'm debating with myself about the ordering of IV and bytes just because of that thing about default values. But I think I'm going to stick with this. And this is the multi-block case here. I'm not going to call it multi-block case because it makes more sense to just call it padding oracle attack. Because, you know, in practice, this is what you would be calling on a given ciphertext. You know, now that I'm thinking about it, I suppose we should take the oracle as an argument here too, rather than just assuming that it's known, even though it is defined earlier on in the file here. So let's make a quick scan over what we have so far, and then we can start filling it in. A lot of unused items. Oh, we need to import optional. That's right, yes. Now this version of the attack, the multi-block case, is fairly simple to define in terms of the single block case, so we'll start here and work our way up. we start with an empty plaintext, and we're going to be appending to this to build up the full plaintext as we go. For each block, we're going to be treating the previous block of ciphertext as the IV for that block, so we're going to keep a running variable tracking what the current block considered an IV is, and that's going to start, obviously, with the default IV. We could, in principle, be taking this as an argument as well, but you know what? Don't think too hard about it. What am I saying? Thinking hard is the entire name of the game here. And there we go, and this is pretty simple to understand. We're just enumerating the blocks of ciphertext, and oh, I should be using my block size variable here just to make this easier to read. And assuming that we've recovered a valid plaintext, it will be correctly PKCS7 padded, and we will be able to remove that padding here. Obviously, our attack tooling would need to account for the case where this throws an error, but yeah, we're not writing that code right now, so for now this is fine. And this is going to be where we're going to have to do our actual thinking in this single block attack function. So I'm going to kick that down the road and focus on the easy functions for now, starting with this encryption function. Now, this would be the challenge as written, would be to use this choice function on strings. However, we have our little embellishment here that we have to account for. And Python makes it so easy to do this with an optional variable. This makes me so happy that you can fit this into one line. And it's so expressive. It's not like some weird, like what C or Java does with their ternary operators. This is actually really readable in my opinion and expressive. Just so nice. And we use the key and IV that we defined above to define this cipher, and then we're going to call the .encrypt function on it. And of course, we need to PKCS7 pad our string before encryption. So that's this function done. Let's do this one. This is going to be basically the same, except it's going to be decrypting instead of encrypting. So we can just copy some of this down here. So we're going to decrypt. And we can make this slightly more expressive here by breaking this out into a separate variable, which I suppose we could also have done up here. So I'm going to do that now. Beautiful. Now for the padding oracle, this is also going to be a very simple function. This one just calls decrypt and then does some logic on the result. We're going to attempt to strip the padding, and this will throw an exception if the padding is invalid, which we then catch. And instead of propagating that, we just return our Boolean as expected. So now already the easy parts of this are pretty much done. And all we need to do is implement the magic in here, and we'll be ready to test this, which is pretty exciting. I was expecting this to be a pretty long recording, and who knows, it still might be. But so far, we're kind of cruising along here. So similarly, we're going to be defining our plaintext at the top level. This actually is not strictly necessary because we're not going to be appending. We're going to be recovering the plaintext all in one go when we finally are able to do so. However, I'll show you why we need to do this once we get into the thick of things. And I'm also going to add one other thing here, which is this zeroing IV. Now, this term I did not discuss in the lecture, although I did discuss it in my original blog post. And this is a term that basically I made up. I have not heard anyone else use this, but I think it's expressive. And it conveys basically the idea that we are, as we go in this attack, building an IV that is capable of zeroing out specific bytes in the plaintext. And the reason we want that is because then you can XOR a given value into the zeroing IV, and you'll be setting the plaintext bytes to that value because you'll be XORing them against that value, and they're already 0, so then that value just gets written to them. And yeah, so that's what this is. This is basically going to be holding intermediate results with part of the plaintext, but not all of it until we finish the attack. But the fact that it holds plaintext bytes is sort of secondary to the fact that it is capable of zeroing the plaintext, which of course by XORs algebra, those are equivalent statements, but this one I think is more relevant to the task at hand. I'll be consistent here. I'll take out those spaces. Like I said, this is capable of zeroing bytes in the plaintext, and so if we just XOR the padding length into every byte in this, the zeroed bytes will be set to the padding length. The non-zero bytes will just sort of be scrambled effectively, but we don't care about that. You could do this so that you were only modifying the zeroed bytes. However, that would make the code messier, and this works, so I'll take simplicity. So we're going to do a search through all 256 candidates for the next byte. And for each one of these, we're going to be writing it into the proper location within the padding IV. Now, the reason that these are both lists is because it allows us to make these modifications to them. Obviously, we're going to convert these to bytes before we pass them into AES or anything like that. But this saves us from having to allocate and deallocate and recreate and append and all of this ridiculous stuff that we'd have to do if we were just working exclusively with byte strings. We can work on mutable buffers here. This is still not as clean from a memory management perspective as you could get in like C or Rust, but it's good enough for Python in my opinion. There's also, I believe, a library that adds similar buffers to Python, but that would be overkill for the level of performance that we need out of this. That is one way that you could optimize it though if you wanted to. And there we go. Now that we've written to this, we can convert it to bytes and we'll get a new IV. This is the one that we're actually going to be passing to our oracle. It's sort of goofy, actually. We take in this IV at the start of the attack, and we're not actually going to use this at any point except at the very end when we figure out the plaintext, right? Because we need to XOR the decrypted plaintext against the IV to get the actual plaintext. But up until that point, we're just going to be making up our own IVs and running the attack in those. And here's where we do that. So we're going to pass this off to the oracle, see what we get. And in specifically the case where the padding has length 1, we need to make sure it actually has length 1. Right? Because there's the case that we talked about, and that is also mentioned over here, that you could have 2 bytes of value 2, 3 bytes of value 3, etc. So we need to rule those out. And in the challenge statement, it's said that you can assume that a 1 in 256 event will not happen. Personally, I'd prefer not to take those odds, because in cryptography, those odds are basically the same as a sure thing. And yeah, I'll just modify the penultimate byte here by XORing 1 into it and run the check again. And this is kind of cute here. I'm really happy with how easy it is to write this. We're just going to continue if this oracle query fails. And what that's going to do is it's going to take us right back up to the top of this for loop. It's easy to forget with all of this nesting. We've got 3 ifs in a row here, but we are inside a for loop. And we can just skip over this byte if it turns out that it was a false positive. And yeah, let me actually, before I get into writing this, let me actually think about how I want to write it. Because we do want to, yeah, I guess we're prepending, right? So we're going to have our candidate XOR the pad length is going to be the actual plaintext byte, right? And then in order to convert that to bytes, we're going to have to put it inside a length 1 iterable and call bytes on that. We could make a tuple here, which would be faster, but this looks nicer. And then we're going to append the plaintext bytes that we've already recovered. And because we're working from right to left, this is the correct ordering of things. And of course, at the start, the plaintext is going to be empty. So this will be a no-op, but that's okay. And then as we get further into the loop, of course, this will get built out. And we abort the search as soon as we find this, because obviously scanning through the rest of the range is useless once we've found our answer for this byte. Important to remember to do that because it'll speed your attack up by roughly a 2x factor relative to scanning the whole search space every time. All right, and this should never happen, but it's a good practice to catch these cases so that you can be aware of how your code's failing and where, and find out as soon as possible when that's happening. And this is an else clause on a for loop, which I guess is a less commonly used feature of the language. This else triggers whenever the loop exits naturally rather than exiting from a break statement. So if you break out, then the else doesn't run, but if the loop runs through all 256 values without ever breaking, then the else triggers, which in this case would mean that we scanned 256 bytes without finding any byte that constituted valid padding, which should never happen. On the other hand, if this exception is not raised, then at this point we know that we've been successful in our search for this byte. We found a candidate that's actually correct, and we know because we hit break at that moment, we know that this variable actually holds that value currently, so we can use it. Like so. And now when this loop completes, down here, we know that zeroing IV will be setting all 16 bytes of the plaintext to 0, which means that this will be actually equal to the plaintext, or it'll be equal to the output from the decryption function, which is technically a plaintext, but which of course needs to be XORed against the IV to produce the actual nominal plaintext that the user put in the first place. So let's just do that here. And great, this is pretty much it, isn't it? This is baby's first padding oracle. And, you know, there's some stuff we could do to clean it up, but for now, let's just try it. We'll put this name guard on here to make sure that we are running this script directly and not just importing it. All right, And I have a feeling something's going to go wrong because otherwise this would just be too easy. But let's see. Okay, that does look to be one of these input strings. I'm not sure which one, but I believe that this is working. Oh, I think it's... Is that it there? Right on. We're getting that as a byte string as expected. So I could just call it done here, but I think we both know that's not how we're going to do this. So let's go the extra mile. So first off, choosing a random one of these is great, and that is what the challenge tells you to do. But that doesn't sit right with me because I want to know what all of them decrypt to. Or excuse me, I want to know what all of them decode to, which is what we get after decrypting them. We have to earn the decodings. So I'm going to add a command line flag here. And you might be thinking, oh, Eli, how are you going to do that? Are you going to use argparse? Are you going to use any of the other 5,000 libraries on PyPy for this? No, I'm going to use this little known library called sys. And watch how I do this, because it doesn't have, for this case, it doesn't have to be any more complicated than this. And I will fight anyone who says otherwise. This is all you got to do. Oh, that was a typo. That should be a -a. Yeah, this will make sure that you've got an argument, and it'll check if -a is one of them, and then it'll run this. So this adds a all argument that we can just use to decrypt the ciphertext in order if we want to. And then, yeah, we're going to do this basically the same after we get our ciphertext. Except that this time we actually know which string it was supposed to correspond to, so we can assert that we've recovered the correct plaintext. And having done that, we will also reward ourselves by base 64 decoding it so that we can see the end result. So now, again, if we run this, we get the expected output, but if we do -a, we're going to get something entirely different. We see that in this case, we're getting ASCII text. In fact, this might even be recognizable to some viewers of this channel. To the rest, all that you know is that it reads, "Now that the party is jumping, with the bass kicked in, and the Vegas are pumping, quick to the point, no faking, cooking MCs like a pound of bacon, burning 'em. If you ain't quick and nimble, I go crazy when I hear a cymbal and a hi-hat with a souped-up tempo. I'm on a roll. It's time to go solo. Rolling in my 5.0 with my rag top down so my hair can blow." And that just about does it for this episode of the Cryptopals Guided Tour. One thing I want to say before we sign off here is that we did not actually touch on implementing the noisy padding oracle case. But if you want to see code for that, I do have some code in my blog post on that. I also have the full derivations for all the Bayes theorem stuff that we talked about. This doesn't go all the way to implementing the padding oracle attack. All it really does implement is the bit of the attack involved in handling a byte search. So yeah, this class does that, and there's a gist on GitHub that you can look at if you're curious. All of this I think is fairly interesting, but it also is a little bit extreme. But all of that basically is a replacement for this in our script here, right? This is the byte search. And that expands out to all of this when you're taking the noisy oracle case, which on the one hand, yes, that's a lot more. On the other hand, I actually think that while it is more, it's less more than it feels like it should be, if that makes sense. It's sort of surprising to me that it's actually possible to handle this with enough code that you can almost fit it on screen. But there we go. I hope you enjoyed this. I hope you maybe learned something. It certainly was quite a lot of fun for me to make this. It's my pleasure to bring these videos to you, and I hope to see you in the next one.